All right, and so welcome to our June 23rd ME316 live lecture. With missing Friday last week, I was kind of looking at our course content and we're able to get caught back up here today. I was looking at lecture notes from last year and was able to combine two of them. And so it'll be about the same link that we had on Monday. And so I guess just a couple of things that are coming up. Our torsion homework is due this Saturday by 11:59 p.m. And I guess, Jordan, do you have any questions over that yet?
No, I don't think so. I was working on that yesterday. I got 4 problems done.
Okay.
Yeah. Everything seemed pretty straightforward.
Good deal.
Just getting lost with some units on a couple of the problems.
Yep, units can be challenging. I did have one email that came in where the student was using an electronic version of Hippler's textbook, and they weren't showing the numbers correctly for the motor problem. Looking at the horsepower, I think it was something like a 1/10 horsepower motor, and on the electronic version it showed 110 horsepower, and so that caused the solution to be different. I think in that scenario where the student emailed me, I gave them the correct information. If it was something where you actually handed that in based on what the electronic version stated, I'll just look at it. It's just going to be an order of magnitude or several orders of magnitude different for the solution in that case. And so I take that into consideration and accept both answers then at that point.
Okay, also on number 16, because of the instructions are find it to the nearest millimeter.
Okay.
And well, my answer came out to 29.42, so I rounded up to 30 because
yes, yep. And so
you rounded down. I just did the quick math, and if you plug that diameter back into the equations, then the maximum shear stress would be 62 megapascals, not under 60, since it's, if the allowable is.
That's a good observation. Anytime you're dealing with geometry, you do need to round up in those scenarios to physically meet those requirements on stress conditions, things like that. And so I guess the other thing I was going to say is I don't think the Friday lecture will be as long. It'll be a little bit shorter. And so Friday would be a good time to ask any additional questions. You can either do that by email, send me questions in advance, or if you show up for the live lecture, you can ask in person. But I'll address any of those questions that come through before Friday for the Friday live lecture. We'll go back to sharing the screen. And always fun working with all these different windows. I'll maximize this for now. We don't need the other thing for just a bit. But on Monday this week, we really talked about just the concept of beam bending, looking at that bending stress as a function of the moment that's applied, sigma equal to MC over I. And we also looked at the area moment of inertia, the I value, which is beam's resistance to bending. For a rectangular beam, we derive that out that the area moment of inertia is equal to base times height cubed divided by 12. And then we can just use that algebraic expression as we move forward with rectangular beams. Then if you're dealing with symmetric areas, you can really add and subtract different cross sections to calculate your area moment of inertia. And so if we have a rectangular tube like this with a base 1 and a height 1, and then internally a base 2 and a height 2, all we have to do is calculate the overall area moment of inertia for the large rectangle, and then subtract off the area moment of inertia for the smaller hollow space that's not there. In that sense, it's kind of similar to calculating the cross-sectional area of, say, a circular tube. You just take the area of the outer diameter minus the area of the inner space, and you would get your cross-sectional area. So it's the same principle that applies here, but for this to be valid, you do have to be dealing with a symmetric cross-section for that to work out properly. And so for this case, our x-axis represents the symmetric or the line of symmetry for both the larger rectangle and the smaller rectangle. And we'll just show that as we go through on being cautious there. So if we do that, the I about the x-axis would just be 1/12 B1H1 cubed minus 1/12 B2H2 cubed. And so that's pretty straightforward in finding the area moment of inertia for rectangular tubes. As we move on to a I-beam, we'd have an overall B1 for the width of the flange, and H1 is the depth of the beam. And then we have a couple cutouts of B2 and H2 on either side of that. And just notice again that both of those, the line of symmetry is running through the middle again. And so all we have to do is take the larger rectangle. I didn't put that there. That would be B1 and H1 on the first rectangle, and then minus 2 times B2 and H2 as we cut both of those out. And so Ix would just be 1/12 B1H1 cubed minus 2 times 1/12 B2H2 cubed. And so that's fairly straightforward to work with rectangular sections like that when the geometry of that cross section is symmetric about the axis that you're bending about. That will not work for non-symmetric areas such as an angle iron or a T-beam, in that there is not then that common line of symmetry for that area. And for that, you then have to use the parallel axis theorem to be able to solve what that area moment of inertia is. And so the parallel axis theorem, that was something you probably covered towards the end of statics. So it's been a while, and I'm not really a good one to commit this to memory myself. And so I usually have to look that information up when I'm doing calculation as well. But what I found is that Hibbler's textbook does a really good job of explaining the parallel axis theorem throughout its appendices A and the back of the textbook. And so this is a good spot to reference if you're ever needing to refresh your memory on calculating the area moment of inertia. And so I think for your 10th edition, that's pages 788 through 794. And we're looking at just a T-beam in that situation that we want to essentially calculate the area moment of inertia of. And there's a process that you go through to do that. first thing is you really need to locate the centroid of the geometry, the centroid of the area. And you can do that. You can define your x-axis however you want. In this case, we've defined that from the bottom of the beam and then y vertically upward through that symmetry line about the y-axis. We just don't have a line of symmetry about the x-axis. And so first off, we need to locate the centroid, and the x bar would represent the distance away from the y-axis that the centroid is located. And the y bar would indicate the distance from our x-axis that the centroid is located. Since it's symmetric about the y-axis, we know x bar is 0. The centroid is located on that line of symmetry. And so all we really need to do is calculate y bar at that point for this case. And that's really just the sum of the individual centroids of each area, the y tilde, times the area of that section divided through by the sum of the total area of the cross section. And so again, x bar, y bar just defines the coordinates of the centroid. The x tilde, y tilde define the respective coordinates of each portion of the centroid, and A defines the area of each portion. And so again, example A1 is nice because it kind of lays this out for you. And I just mentioned that since it's symmetric about the y-axis, x bar is equal to 0. And then we can look through then on our example problem on the y bar. We'll expand this out so it's a little bit easier to see. And so again, y tilde times A for each of the portions divided by the sum of A. And let's see if we can bring that back up. No, I did not show that. So again, the area of this first, I did number 1 up here on top. So the distance to that centroid would be 11.5 inches. 10 plus 1.5 times that cross-sectional area. 8 times 3 is 24 inches squared, plus then 5 inches for the y tilde there, times its cross-sectional area. 10 times 2 is 20 inches squared, divided by that sum of area, 24 inches squared plus 20 inches squared. Will give us then our y bar of 8.55 inches. And so that defines then that distance to the centroid of the area. And then this would correspond then to that neutral axis that we've defined, so that in a state of bending about the centroid bending along this x-axis, that location would be the neutral axis location. Well, let's see. Then we'll kind of continue on. Then you can use the parallel axis theorem to solve what Ix is. And that's really just looking at the moment of inertia of each of the individual portions, plus the area of that portion, times the distance between the centroid and the centroid of each of the portions, that distance squared. And so now we have this x prime defining our centroid, And so again, all we're looking at is the area moment of inertia of each section itself. So this would be the BH cubed over 12 for each portion, the IX prime with the bar on it. Then we add then in the area plus the distance that we have between the centroids of the area and of the centroid of the total cross section. Notice that that distance is squared, so it doesn't matter if that's a positive distance or a negative distance from the centroid. Since it's squared, that'll always turn out as a positive value. And so slide 4 just kind of shows that then looking at that for each of the sections. And calculating the area moment inertia out as 646 inches to the fourth. And so do go back and look at those numbers that they're using there. And again, it as I was discussing that, I was just describing that for each one. An alternative way to do that is to look at the base times height cubed over 12 of the entire section, and then subtracting out 2 of the smaller sections. You really don't gain a huge benefit in this particular problem because you do have to use still the parallel axis theorem to subtract out these sections. Since that's not symmetric about the centroid, the parallel axis theorem still has to be used in that. It's just showing that you're able to do the same thing with subtracting out sections. You just have to do so using the parallel axis theorem. I guess, Jordan, does that kind of, do you have any questions on that in terms of utilizing the parallel axis theorem?
No, it seems familiar. I remember doing this in statics.
Okay, that's good to hear.
It wasn't on the final, so.
Yep. And so also just remember, that's my go-to source. If I ever have to do this, I tend to just go to the back of Hibbler's textbook just to refresh my memory. Because this is something that I don't often do. The things that I have committed to memory are just what the area moment inertia is for a rectangle, BH cubed over 12. For a circular section, pi d to the fourth over 64. So those things are committed to memory because you're generally dealing with common cross sections like a rectangular or circular tube when you're designing things. So those things are easy to commit to memory, but then these things not so much. So you need to know where to look to find that if you can't remember it off the top of your head. And then you can do some sleight of hand tricks too that are pretty nifty. Example A3 talks about a section. Again, this is an odd section that you probably would never come across often, but if you were to come across this, you could solve this using the parallel axis theorem as we did before, and that's the way your book solves it there in example A3 is using the parallel axis theorem. But there is an easier way when you have geometries that are shaped like this. You can shift portions of the geometry as long as it does not change the distance between the centroids of the overall area and the centroid of the portions. And so for this particular case, if we're looking for I about the x-axis, we could really just move this portion on the right-hand side and slide it over here to the left-hand side. Since we're not changing the location of this centroid respect to the x-axis, we're still going to get the same area moment of inertia out. And then with that, we have an overall base and overall height for our larger section. And then we have the smaller section. Let's see. I think I have the overall section here. Now I'm subtracting off the smaller rectangle to the right of it and then adding that other one back on. And so that's a 3-step process. You could have just added 2 sections, the long, tall rectangle, and added then that small section. So you could do that in either step. And so with that definition, this first big rectangle would be base times height. The second rectangle would be a base minus the t, and the height would still be h. And then the third rectangle would be base minus t, and the height is also t. And so it's just going through and solving that. And when I did this originally, I was just saying 1/12 bh cubed over 12 and not really specifying what each one of these bases were. So I put that in pin up here, that for the second one, that base would be b times t as defined. And for this third one, the base would be b minus t and the height would be t. And so just plug in the values for that, and you end up with the same value for the area moment of inertia about the x directions, 2.9 times 10 to the 9th millimeters to the 4th. The answer that they give there for example A3. The nice thing about this method of shifting the geometries is I didn't have to remember the parallel axis theorem. I was just able to remember the bh cubed over 12 and shift things around so I could solve the area moment of inertia without having to look up the parallel axis theorem. And then same thing for IY. If we're rotating that or bending that about the y-axis, we're essentially shifting, say, the lower portion up above. In that process, the distance to the centroid switches signs, but the magnitude remains the same. And since that distance is being squared, the sign is irrelevant. And so we end up with a U channel then at that point where both of the geometries, we have the overall rectangle that we can solve I for and then subtract off the smaller rectangle. And again, you get 5.6 times 10 to the 9th millimeters to the 4th, same that's they got with the parallel axis theorem, just a little bit quicker. And this method of shifting the geometries like this will get you the correct area moment of inertia calculation out, but the non-symmetric nature of the cross-section that we have will reduce and create non-symmetric bending. And so you'll get some twisting out of that. So although this works for calculating your I of x and I of y values, this really results in unsymmetric bending. And that's special topic covered later on in section 6.5. And so we don't have to worry about the unsymmetric bending aspect, but being knowledgeable to be able to solve what the area moment of inertia is will hold you accountable for that. Then when you're dealing with composite beams where you have two materials, to solve the area moment of inertia for that situation, you really need to transform one of those materials as if it were the other material, so they can find the area moment of inertia if it were a common material. And so in order to do that, we just need to find the equivalent width of the other material. And so for this case here, where we have a material A and a material B, where BA is equal to capital B at the bottom, and they have the respective heights, the magnification ratio is just that ratio of the Young's modulus of material B to material A. And the way we transform that then, if we're looking for I about the x-axis, is again, we don't want to change where that location of the centroid is for that section. So we only want to change that in the width direction, so that centroid of section B remains the same as if we expanded it out to all material A. And so that new width is just that magnification factor with the ratio of the Young's modulus times that original width that we have. And so this product then would be the equivalent width if the material were A. And so one thing you do find is this does cause a shift in the neutral axis, and it transforms this rectangular beam of two materials into a T-beam, essentially. That would be the one common material. And so for concrete reinforced with steel, when you're looking at a roadway, as trucks are driving over, that's placing a load down. So the lower portion of the concrete would be in tension, whereas the top of the road surface would be in compression. And so concrete is a brittle material, and it's able to withstand compressive loadings well, but not tensile loadings. And so when you drive by a construction zone, you'll notice that they'll put the steel rebar towards the bottom of the concrete pour. And they do that so that the steel is able to absorb those tensile loadings near the bottom of the structure. And so typically for concrete, what you're doing is you only account for the concrete in the compressive region. For the tensile region, you just assume that that is not going to be carrying any load at all in a tensile manner, and you account for that all with the steel, the rebar that's located in that region as carrying the total load through that section. Let me see what figures I have. Oh yeah, this explains that well. And so this goes back then to this discussion here. This would be a concrete with the steel rebar running through near the bottom. And so in this situation, again, we're assuming that the steel is in tension, and then the upper half of the concrete above the neutral axis would be able to support the compressive loads. And so this other concrete below the neutral axis is not taken into consideration in the load carrying capabilities. And so what you then end up with is a situation where you have your concrete cross-section, and then you look up the equivalent width of that steel that's in that area down there to determine what that equivalent width is if it were all made of concrete. And so then you get this weird shape where you have the steel in the bottom portion, the concrete in the top half, but it's transformed as if it was all concrete. With that, then you can then solve the area moment of inertia You would have to use the parallel axis theorem to do that, since those areas are non-symmetric about the neutral axis. And we have NA there to designate neutral axis. And I think we're good with our PowerPoint there. And so here's just a quick example. This is a problem in the back of the, or problem in the book at one time, but we have a rectangular wooden section that is sandwiched by two steel plates as shown. The total height of the wood is 150 millimeters and each of the steel sections is 15 to make it a total of 180 millimeters in height. And originally they're both 100 millimeters wide. And so what we want to do, given the Young's modulus of both materials, and if there's a moment applied of 30 kilonewton meters, we want to find sigma max in the wood and the steel. And I'll kind of show you that. We use this ratio then to find the equivalent width. But once we know what our area moment of inertia is and calculate the stress as if it were all that one material, then we have to transform it back to the original material that is a smaller width. And so this example problem will show that process. And so what I did was just calculate an N of the E of the wood over the E of the steel. 10 over 200 will give you 0.05. And so the width of the steel, if it were wood there, would be N times BW, 0.05 times 100 millimeters. What I'm doing is transforming the wood into steel. And so that's just going to narrow that considerably. The alternative would have been to calculate this top portion if it were wood, and that would expand that out in both directions. So you really have both, either method that you could do. This one, I shrunk down the wooden section to account for that as if it were steel. And so that would be 5 millimeters thick for the steel section. And so I is just 1/12 B1 H1 cubed minus the two sections over 12 times B2 H2 cubed. And with the geometries, you can plug the values in and get the area moment of inertia out for that cross section as if it were all steel. And so once you know that area moment of inertia, then it's just like we did on Monday. The stress in the steel, the maximum value is just MC over I. And I did convert our 30 kilonewton meters over to 30 million Newton millimeters. So that we could have that unit of force in newtons, unit of length in millimeters, and then our stress would come out in megapascals. And so with that, C value would be the distance from the center to the outer edge for the steel. And so 150 plus 30 is 180 divided by 2 is 90 millimeters. That's our C value. And I we just calculated. So the maximum stress in the steel portion we get is 123 megapascals. Then if we look at the stress in the steel for that wood section at 75 millimeters from the neutral axis, this is the stress if it would be if it were steel. And so same thing, we're just plugging in 75 millimeters for that C distance. And so if this were all steel, that would be 103 megapascals at the top there in compression. And then it would be 0 at the center and 103 megapascals in tension at the bottom. But for the real geometry, it's not steel, it's wood. And so that stress of 103 megapascals is confined to a 5 millimeter space. And so when we expand that back to the wood, it's distributed over a much larger area. And so our stress in the wood for that would just be that magnification factor times the stress in the steel we just calculated. So 0.05 times 103 megapascals will give you 5.14 megapascals. And so the distribution in stress then is 123 at the top and bottom of the I-beam, essentially, of the sandwich structure. And then it drops down in a linear fashion to 103 megapascals. That is just in the steel portion just above the web. And then it drops down to 5.14 megapascals since it transitions to wood, and the wood is carrying much less of the stress in that range. And then it goes in a linear fashion, 0 at the center and 5.14 again once it reaches the bottom of the web. But that ratio, just look at the Young's modulus values. If the wood is a lot less value for the Young's modulus, that's going to shrink that when you transform it to steel. Likewise, since steel has a Young's modulus much greater than the wood, that would expand the steel width out if you were to have solved it that way. So either way, you would get to that same profile then for the stress distribution through the thickness of that composite beam that's comprised of wood and steel. The one nice thing about this problem was that the wood was sandwiched by both sides with steel. And in that process, everything was symmetric. So we're able to just add and subtract off the cross sections. If you'd only have like steel on one side, that's going to create your T-beam again. So you'd have to go back and use the parallel axis theorem in those cases. Let's see, do you have any questions there, Jordan?
No, I don't think so. Seems relatively straightforward.
All right. And so that concludes our discussion on the bending stress that develops in the beam based on that internal moment that develops. And we have also talked about that internal shear force that develops in a beam, and that's going to result in a transverse shear stress. And so that's the topic of chapter 7, is that transverse shear stress that develops within a beam due to the internal shear. And there's a couple ways to kind of describe how that transverse shear stress develops. One, it's just there's a shear force there, so obviously you're going to have a shear stress. And in that designation for our internal shear, I like to put the horizontal lines on top of the V to indicate that's a capital V. When we get to chapter 12 next, we'll jump ahead to look at deflections of beams. We'll deal with the vertical deflection, which your book uses a lowercase v. So the line over the top on the shear force really helps designate that as the shear force. And so when we look at deriving this, we are going to look at, again, the base and the height of, say, a rectangular section. And in solving the transverse shear stress, we'll need to solve a Q value that we'll get to, but that really just looks at looking at a distance y away from the neutral axis, and you would be calculating your transverse shear stress at that distance y. And when you're doing that, you're just solving the area A prime above that location. And we'll also find that instead of using base, the shear formula uses the thickness at that section. So if you're having a varying cross section, you would use the thickness, the width at that point where you're solving the transverse shear. And so if you take a first order stab at it, you could say that the average shear stress that develops is just that shear force divided by the shear area, which would be the base times the height. And so that would be more of a direct shear approach to solving that shear stress that develops with the average state of shear stress in mind. But what we'll find is this is a non-uniform shear stress that develops. And so this is not accurate looking at that as an average shear stress. And so we'll take you through and show you that reason why. And so again, solving an axial shear at distance y from the neutral axis, the transverse shear formula is equal to our shear force V times Q, which is the first moment of area above that point y that you're looking at, divided by I and divided by the width T, which we have been using base previously, but the shear formula defines that width explicitly as T, just so if that varies along the y-axis, you can take that into account. And so the good news is we already know what the shear force is. We've created our shear and moment diagrams from what we've done in chapter 6. And you can identify what your maximum shear force is along the length of the beam, and then correspondingly calculate your maximum shear stress. We've already done that in chapter 6 with our area moment of inertia. T is just the width of the member where your shear stress is determined. And so the only new thing that we have to look at is that Q value, the first moment of area above Y. And this gets into another area that you don't commonly include this in the analysis. So it's easy to forget. And it's just a matter of looking back at your notes or the textbook if you're concerned about this and needing to take into account the transverse shear stress. But Q is units of length cubed, so inches cubed or millimeters cubed. And it's the integral of y times dA prime. And so the integral of y times dA prime is just equal to the y bar prime, the distance to the centroid of that cross-sectional area, times that cross-sectional area A prime. And so that would give you then the shear stress at that distance y above the neutral axis. If you're dealing with multiple geometries, where looking above y, you have, say, another thing jutting out, it's really just the sum of those distances to each one of those center of areas times the area of that portion. And so we can derive this then. What you'll find is then that that shear stress is going to vary with the distance away from the y-axis. And so you need to know what that distribution is through the thickness for the cross-section. And so for this, the Q is just y bar prime a prime. And so y bar prime is just going to be that distance y plus 1/2 of h2, h over 2 minus y for the y bar prime. And for this geometry, we've really just set things up so that this is located about the neutral axis, and for our height of the beam, we just have that centered about our neutral axis. So h over 2 on top minus h over 2 on the bottom. And so we're again just going to the centroid, y plus half this distance, this will get us to the centroid, times then that a prime. It would be h over 2 minus y would give us that full height of that cross section, times b would give you the width. And I'm going to present this in terms of h and b so that when we combine things at the end, our b values will cancel. And so we'll say our t and our vq over it formula, we'll just plug a b in there for that. And so that sets up our basic relationship. And then it's just algebra going through and solving for that. First step, I multiplied the half through to get h over 4 minus y over 2. And then everything else is just the product all the way through. We have a y minus a y over 2, which will give us a positive y over 2. And then we can pull a half out of all that, the first expression that we have there. So we'd have a half, and I then moved the h over 4 first, so we have h over 2 plus y then. And so that half was just pulled out of that first one. And then we have positive h over 2 plus y times positive h over 2 minus y. In that situation, you can simplify that down to an h squared over 4 minus a y squared when you do the cross multiplication. And so q then is equal to 1/2 h squared over 4 minus y squared times the width of the rectangle, b. And so what we find is that q is the quantity then that varies with respect to y in our transverse shear formula. Shear stress is equal to VQ over IT. And so this is what makes that shear stress vary with respect to the y-axis. And so one thing to note on that is at the top and the bottom of the beam, when y is equal to h over 2, we'll end up with h squared over 4 because the 2 gets squared as well. And so we have an h squared over 4 minus an h squared over 4. And so that tells us that the shear stress or the Q value is 0 at the top and the bottom of the beam, which then tells you that the shear stress is 0 at the top and the bottom of the beam. So that's where the shear stress is 0. If we want to look at where the maximum value is, remember anytime you're trying to find a min or max, take the derivative. And so dq dy would be equal to a minus y times b. We'd get in the derivative of minus 2y, and then divided by 2 will just give us a minus y times b. And so we'll find that q max to locate a maximum value, taking that derivative, setting it to 0. That would only occur, the width is not going to be 0, otherwise there would not be any geometry. So that only occurs when y is equal to 0. And so we get the maximum transverse shear stress occurring at the neutral axis. In addition to that, we see that that's a second order relationship. So we know how that varies through the thickness as well. It's a second order polynomial. When we put y equal to 0 in for q, we'll end up with a h squared over 8 times b. So Q max is equal to BH squared over 8. And now we'll see why we use that as B here. We're kind of comfortable using that already. And so tau max then is equal to V times Q max over IT. And so we have V, Q max is BH squared over 8. I is equal to BH cubed over 12. And the thickness again is just equal to our base for this common rectangle. And so our bases, we have 2 of them that will cancel. Top and bottom there, we'll have an h squared that will cancel with an h cubed. And we have 12/8, which is 3/2. So we still have a base and a height in the denominator. And so we end up with 3 times the shear force divided by 2 times BH. And remember again, our average shear stress was just V over BH, our shear area. And so our BH is really referring just to our shear area or our cross-sectional area. And so we're left then with 3V over 2 times our shear area is our maximum shear stress, which tells us then that our maximum shear stress is equal to 3/2 times our average shear stress. So tau max is 1.5 times greater than if we were to just do a direct average shear stress type of calculation. And that's valid for a rectangular cross section. And so one thing to note about that whole process is that tau max is a maximum at the neutral axis, where the bending stress is equal to 0. And then the shear stress is 0 at the top and bottom of the beam when your bending stress is maximum. And so this makes it a little bit easier for a combined loading aspect, since when you have your maximum normal stress due to bending, you don't have a shear component. When you have your maximum shear stress at the center of the beam, you don't have a normal stress component. So you can really evaluate those 2 components separately, whether they meet the criteria that you're trying to design for, and not have to combine those loadings. If it's just a case of bending with your transverse shear. If you start adding in other loading components like axial loading, torsional loading, then you'll have these things combining with one another, and you'll have to look at that from a combined state of stress standpoint. And so to summarize then, just looking at the relationship for common cross sections, when you look at a rectangular section and we take an element out, if we have a shear force acting down, that'll place a tau xy acting down on that face, and it's going to be 0 at the top and bottom, maximum in the center. The way they usually designate that is just by showing that polynomial second order relationship for that. This is for rectangular base times height. Again, tau max occurs at the neutral axis where y is equal to 0. And that is 3/2 times tau average. And then tau is 0 at the top and bottom. Similar relationships can be defined for a circular cross section. That's a solid circular section. It's not as severe as a rectangular section for the magnitude of the maximum shear stress in relation to the average shear stress. It's 4/3, so a 1.33 instead of 1.5. But then for a circular tube, it's worse than a rectangular section. It's 2 times greater than the average shear stress. And again, both of these are set up that they would be in a quadratic type manner. And so for both of those, again, it's going to be maximum at the center and 0 at the top and bottom. That's one explanation for the shear stress that develops. We have a shear force, so we get a shear stress. And then the other explanation kind of looks at if you were to look at a free body diagram of a beam as it's bending, we can look at a section of that, and the full beam is base times height. And so if we were to look at, say, the top portion of that, the moment is increasing as we're going up. So if we were to look at that, we would have a moment on the left side and then a moment plus dm on the right-hand side equal, I'd say, opposite in magnitude and slightly greater in magnitude going in the opposite direction. And so if you sum your forces in the x direction, you'll have more force going to the left than to the right. So you'd need a shear force along that bottom face, or a shear stress along that bottom face to counteract those normal stresses that are developing. And so that's the other explanation as to why a transverse shear stress is developing. And if we look at that element A, that is occurring all around that element. But when you look at your chapter 7 textbook, chapter 7 in your textbook, what this transverse shear stress leads to, say in wooden members, is a shear stress at the neutral axis that can lead to a crack running the length of the, say, a rectangular beam located at the center of the beam. And that's due to the transverse shear stress component as that's trying to bend and developing those transverse shear stresses. And so that is a really good point to stop and take a rest. I guess, do you have any questions at all?
Don't think so.
And so as we come back, we will make use of this derivation previously for a rectangular section and use that to solve a problem. But I can stop sharing now. I can stop recording, and then we can get back together in 5 minutes. All right. Thanks, Jordan.